Slight change in terms of the technology, I suppose, or the particular kind of technological area. But oops, sorry, hang on. But actually, in many ways, the kind of context is much the same. So what I'm very much interested in here is how we go about recycling of waste solar panels, so when they reach their end of life, but more particularly how we can actually reuse the materials that have been used within those panels, such that we can really kind of work towards very particularly going to be looking at how you go about, or the possible methods for the upcycling of silicon itself. So once you, so the method that you can, the idea is to extract that from the waste panels, the end of life panels, and then having done that, you need to do something to make it so that you can then turn that silicon back into useful, valuable solar cells again, which you can then repurpose. You can put those back out in the field. How do we do that in such a way that we end up with this kind of circular economy idea? Oh, there we go. Okay, so just a quick overview. I'll kind of go through a introduction, a little bit of a crash course in photovoltaics. Nothing too technical, hopefully, but just a kind of bit of an introduction to what they are, how they work, and why we're interested. A little bit on the problem with PV modules generally. The kind of this idea about recycling of panels versus the upcycling of panels of the materials. So at the moment they can be recycled, but they're not necessarily, you don't end up with something which is better than you started with or as good as you started with. So then a quick look at this kind of idea of module mining, if you like, so waste mining, which is quite common in some of the kind of more technological areas, and kind of silicon upcycling as a function of that, and then some conclusions at the end. Okay, so a kind of crash course in photovoltaics. Well, first of all, what are they? Well, they're devices made from a range of different materials. But really the key one, the kind of key thing, is that these are semiconductor-based devices that convert light. There's a direct conversion technology that convert light into electrical energy. So it's a means of generating electricity directly from light. And the key one really is silicon. Silicon is the primary technology. It's by far and away the most used technology. Silicon devices have something like 95% of the market. There are various others, and for various reasons they don't really get used, and they tend to be a bit more complex, certainly from a recycling perspective anyway. So actually, in many ways, the fact that silicon is the kind of most used technology for this is actually not necessarily a bad thing. So what do they look like? This is a research device, but this is very much set up in the way that a standard module would be. It's a single cell rather than multiple cells, which is what you would typically have in a module. And this is an alternative technology. This is a research device, so cadmium telluride device. So you get different sizes, types, designs, and so on. But really, it's these things. This is the silicon cell. This is what we're really interested in today. Okay, so first of all, why do we care? What's the point with photovoltaics? Well, as I mentioned, they're a direct energy conversion device, so they convert light directly into electricity. That's really useful because it means that we can use sunlight to produce electricity, which we can then use for all the things that we use electricity for. So it's a very valuable technology. If we think in terms of the resource we have available to us, the incoming solar resource is around about 174 petawatts. So that's the amount of energy which continuously hits the top of the atmosphere. That's the amount of light and heat energy, sort of electromagnetic energy coming from the sun. And that's the amount that hits the top of the atmosphere constantly, really. It's not absolutely constant for various reasons, but it's not too far off. But the key thing really is that this is far more energy than we use as a species in any given year. So it's over 10,000 times the amount of our annual energy use. It's a really, really massive resource. There's a huge amount of energy there. What that means is that it's a very plentiful and effectively, from our perspective, effectively infinite clean source of energy. It's a non-carbon emitting energy source. There are some problems with it, not least that there's a distinct disparity, a definite shift between when the resource is available and when we actually want to use the energy. So the resource and the demand don't necessarily, so supply and demand don't necessarily match up terribly well. They can do, but particularly in winter, they definitely don't tend to. Particularly when you get the further you get from the equator, particularly in winter, you tend to get a fairly significant disparity. And it's quite a dispersed energy source. So the resource is quite large on a global scale, but it's dispersed across the entire planet. So it's not necessarily easy to collect in any one location. That makes it a bit more challenging to capture because you need to put panels in lots of different places to get as much power as much energy as possible. Excuse me. And whilst panels are increasingly cost effective, solar modules are still relatively expensive. That said, they have come down in price quite considerably. And actually at this point, an awful lot of the cost of installation is actually more to do with paying people to do it and things like cost of scaffolding, if you're putting it on a roof, those sorts of things, what we refer to as balance of systems, rather than the module itself. That said, the module itself is still a significant cost, so it's still quite an important cost within the system as a whole. It's also worth noting that PV modules have quite a lot of embodied energy in them as well. And they contain quite a lot of useful materials. So the fact that the cost of the thing has been coming down, it's still quite important, in my opinion at least, to recycle these things and to reuse those materials as best we can. Okay, so in terms of the modules themselves then, there are various kind of issues to do with how they're produced, which make it quite challenging to actually recycle them. So a little bit of background. The key thing with this really in terms of the recycling is that the installed photovoltaics capacity has been increasing really, really rapidly. We've been going, so the amount, the volume of photovoltaic panels installed has been increasing approximately exponentially for a bit over a decade at this point. So what does that mean? Well, it means that there's increasingly significant quantities of these devices, of these panels, producing electricity, which is a good thing. The downside is that these modules typically have a lifetime of around about 25 years. It can be longer, can be shorter depending on what happens, but it's usually around about 25 years. So this is a really important point from a recycling and an upcycling perspective, because it means that in the next decade or decade and a half, something of that nature, the number of modules which we will need to deal with, so the amount of waste modules in effect, will also increase exponentially, just at a 25-year lag from when they were installed. So at the moment, it's not too big a problem, but it's definitely something that we are going to run into as a major waste stream in the coming decades. And it's definitely something that we will need to deal with. Okay, so why does that matter? Well, silicon is the second most abundant material in the Earth's crust. It's not rare. So on the face of it, you might think it doesn't really matter all that much. The difficulty is that the refining process, the process of actually producing that silicon in the first place, involves the reduction of silicon dioxide using carbon. Silicon dioxide is very common. It's a very common rock forming material. It's the primary component in window glass, so we're not short of the stuff, but it's very difficult to remove the oxygen from. And as I say, that's typically done using carbon and actually usually using coal. So whilst photovoltaics are a really good renewable energy technology, and the electricity that they produce is carbon free, the actual production of the module does involve a certain amount of CO2 emissions, CO2 production, particularly in terms of the actual generation of silicon itself. It's a very energy intensive process, and the initial production process does involve using coal typically, or certainly carbon. Once you've got that initial process, that produces what's known as metallurgical grade silicon, which I'll go into a little bit more kind of, not detail exactly, but we'll discuss that a bit more later. Metallurgical grade silicon is relatively impure, so it's the kind of initial material. That's fine, but in order to produce any sort of silicon device, be that solar cell or electronic devices, computer chips, and so on, you actually need much higher grade material. You need much higher purity. So if we're talking about solar grade or very high purity silicon, the refining of the metallurgical silicon to that high grade is really quite energy intensive as well. That's typically done using a thing called the Siemens process, or a variation of the Siemens process. There are various other kind of equivalent processes, but they all work in a fairly similar sort of way. They all tend to work with a particular material called silane, which is a very unpleasant material, and I think it's toxic and explosive, I think. I believe, but either way, it's quite a nasty material to work with, and it involves very high temperatures and quite significant energy input as well. So it's really not a good process. It's the most effective way that we have at the moment for the refining of silicon, but it's really not a good process to have to use. The various other alternative technologies, they all have their own problems, their own difficulties. None of them realistically are going to overtake silicon anytime soon. And on top of that, they mostly also include a number of unpleasant materials and so on of their own as well. You can recycle some of them, cadmium telluride in particular, which is the only commercially viable alternative to silicon, does actually have a complete recycling process which is in use. But at the same time, it's unlikely, for a number of reasons, it's very unlikely to actually displace silicon as the primary module technology. So actually recycling of silicon is actually probably the more immediately important, or kind of, the more kind of pressing concern. Okay, so in terms of module recycling then, what is it we're actually doing? Are we recycling it, or are we upcycling it? I believe Ricardo was saying in the last talk that upcycling, we tend to consider that these days at least to be the idea that you're producing something which has a higher value, or higher quality, if you like, or value than your starting material, or at the very least it should be the same kind of quality as what you started with, if not better. So recycling quite often doesn't do that, and that's certainly true when it comes to photovoltaic modules. That said, the recycling problem, if you want to see it in those terms, is primarily economic. It's not really a technological issue so much these days. Most of the materials, we've actually worked out ways of extracting them from a module. It's just not always economic to do it, which in itself is a problem. But we can get all of the glass, the metals, silicon components, and so on from a module. In theory, we can fully recycle them, and they can therefore effectively be infinitely reused. You can get into this kind of cradle to cradle idea, and you can reuse that. If you think about glass, for instance, we already do that to a large extent with glass in various forms, think glass bottles and so on. Metal, similarly, aluminium, steel, and so on. Again, we have pretty good recycling streams for that, which do effectively just continuously reuse the same material in some form. In terms of PV modules, though, this doesn't mean that they are actually properly recycled. So at the moment, the standard kind of processes, and there are various people who are introducing new processes on a commercial basis, but the standard current processes typically involve recovery of the aluminium frame. So most modules have an aluminium frame as a kind of support material around the outside. So that can be cut off, and that can be taken straight into your aluminium recycling process, recycling stream. So that's fine. There's also, they typically have a thing called a junction box on the back, which is essentially where the electrical connection comes off the device. That's got quite a lot of copper wiring in it. So that can be removed. Copper is a reasonably valuable material, and that has a very high proportion of copper in it. So that's taken away and that's recycled. That's great. That's all nice and well and good. The difficulty, though, is that once they've done that, because of the way photovoltaic modules are produced, the idea is that these things are supposed to sit outside in whatever weather conditions get thrown at them for 25 years. So they're actually designed to be really difficult to separate, which from a recycling perspective is a pain, because it means that actually getting at the materials inside the module is quite hard work. So at the moment, from the kind of standard thing that a lot of recycling plants will do is they will take a module once you've got rid of the junction box and the aluminium frame. The rest of it then just gets crushed, turned into a sort of gravel. And really, there's not very much you can do with that. It's essentially kind of contaminated glass colored. At least that's how it's typically considered. And as I say, there aren't many things you can do with that. The kind of primary one it gets used for really is just as a building filler material for construction, which is a bit of a waste really, because there's a lot of extra things in there which you can make significant use of, and there's a lot of embodied energy in there which you're essentially wasting. There is also a fairly significant elephant in the room, which we've not mentioned so far, and that is that all of these modules contain some sort of polymer, some sort of plastic polymeric material, which at the moment, these are not really readily recyclable. So if you look at a typical solar module, let's see if I can bring up a laser pointer. There we go. Hopefully it makes it a little bit easier to see. So you always start with some sort of a cover glass, a glass sheet on the top. You then typically have an encapsulant material with your cells and the interconnections between the two. So within that encapsulant, so you have two layers of that. That encapsulant is typically a thing called EVA, which is a particular polymer or set of polymers. You then typically have a polymer backsheet. Sometimes they use a sheet of glass, but usually it's actually a polymer, and it's usually some sort of fluoropolymer. So typically a thing called Tedlar, which I think is made by DuPont, but it's a fluoropolymer. The reason you use that is because it's very water resistant and it's quite a strong material, kind of a weatherproof material. And then you have an aluminium frame as well. But the problem really is that none of these polymers, the fluoropolymer and the encapsulant, they're not really readily recyclable using current processes. Okay, and this cell that I showed before is very much an example of this. So admittedly, this is a research cell, but this is made in very much this style. So you've got the white, it's a bit difficult to see, but you've got the white material at the back. That's this Tedlar material. This is this fluoropolymer. Then you've got a transparent EVA adhesive, which kind of sticks the whole thing together. You've got the cell in the middle. The thin lines on the cell are silver. That's silver electrical contacts, which remove the current from the device. And then you've got the metal bars that you can see. They're a silver color. It's actually copper, but it's copper which has been covered in a solder material. So the idea is that you can actually solder those wires, the bus bars, directly onto the cell quite readily. But the actual device, the actual material itself in those metals is primarily copper. And then you've got a glass cover sheet as well. And the whole thing is then that whole sandwich is put together and then it's laminated using essentially just a very large version of the sort of thing that you use for laminating paper. It goes to slightly higher temperatures than that, but the concept is very much the same. Okay, so I'm just very conscious of time, so I'm going to run through this bit a little bit quicker. So one of the things really that we can think about in terms of modules is that they're quite a good resource. So a waste module is quite a good resource. So we can think of it in terms of mining. So if you think in terms of what a module consists of, what it contains, well, the kind of key parts really from an economic perspective, you've got the silver. Silver it's a relatively minor part of the module, but it's probably one of the more expensive parts. So that's actually economically really quite important. The tabbing strip, so that copper metal coated with the solder, that's again, copper is quite valuable. So and there's a relatively high proportion of that within your module. And then of course there's the silicon itself. And actually arguably the silicon cells are the most expensive part of the module, not in terms of the material, but in terms of the amount of effort that you have to go to actually produce them in the first place. And it's probably also worth being aware really that the proportion of silver and copper in a typical module is actually higher than quite a lot of commercial ores. So in particular, I'm not sure with silver. Silver, you're typically looking at sort of parts per million, or parts per thousand at least, in terms of kind of levels before an ore becomes commercially viable. With copper, it's sort of 3% or less is often quoted, or you can go to quite a lot less than that, and it will still be, under certain circumstances, can still be economic to mine. Those proportions are, it's typically higher than that in a module, or can be higher than that in a module. So actually, if you can compare them with an ore, they're pretty high value material, really, or can be quite high value material. And as I mentioned before, silicon is abundant, but if we were to extract it from old modules, this would very much reduce the energy requirement for the production of further silicon. It would also quite dramatically reduce the amount of carbon dioxide emitted by the production process, because it wouldn't require the use of coal or a carbon source to reduce the modules, so the silicon material from the silica. So I'm just very aware that I'm starting to run over, so I'll go through this reasonably quickly. There are various different methods which can be used for separation of the different materials and different components. Density separation is probably the most effective, and this can be automated, so you can do it as a wet or a dry process. And the advantage of this is you can actually do it from a crushed module. The other processes mostly require the different components actually to be relatively complete. But doing it from a crushed module does make life a lot easier, because it means that it makes the whole thing a lot easier to automate. It makes the whole process easier to actually do using existing recycling facilities. The extracted silicon can then be treated as metallurgical grade, so you've kind of gone in at that point in the system typically. This is still a little bit of a problem, because you still require refining of that material to produce useful solar cell feedstock. So what does that mean? Well, one of the problems is then that refining of the end-of-life silicon cells to produce high-grade silicon is still not necessarily economically feasible during the recycling and recovery process. Producing metallurgical grade silicon can be, under certain circumstances, and if it's done right, particularly if you have an automated system. But the production of higher grade material is still not necessarily economically feasible, which is a shame, because that higher grade material actually has a much higher value. So if we can find a method of getting there which doesn't cost too much, which has a lower energy use, then that could actually massively improve the economics of the recycling process. So yeah, that could be resolved through cheaper means for the refining of silicon. So I mentioned silicon is usually refined using this thing called the Siemens process, which is a complex high temperature process, and it's potentially dangerous. It's energy intensive. It's used quite extensively within the silicon manufacturing process, but the problem as well is that it tends to be in large centralized facilities, and it's not necessarily something that can be done readily at a kind of recycling plant, really. So in terms of how we go about kind of the upcycling or the refining of that silicon material to produce the higher grade material, which we can then use for the production of high quality devices or new high quality cells, there are various different ways you can in theory do that. My kind of preferred technique or option would probably be to use an electrolytic process. So what do we do with this? Well, we actually use this in many different locations, for many different materials. A kind of classic one is the refining of copper, which you can do using a copper sulfate bath. And essentially you have your unrefined copper material on one side, you've got your kind of your refined copper on the other. You put an electric current across the two devices, or the two materials. The copper goes into the bath, and you get copper coming out on the other side. You get pure copper being deposited on the other side. You get some impurities then end up being dissolved into the bath, and a lot more of them then kind of end up as a sort of sludge on the bottom of the bath. So it's quite a good way of actually refining your material. But there are problems with that. There's no fundamental reason why you can't purify silicon that way, but you can't necessarily do it in an aqueous electrolyte, so there are problems that way. Ideally, the complete process would also include the separate recovery of silver in particular. Copper can be extracted through the density separation, but the silver is actually kind of it's embedded in the top of the device. So you would need some additional process for the removal of that, particularly as well because that's quite economically quite important in the recycling process. But then in terms of actual electro winning or the electro deposition or kind of electro refining of silicon, people have done this. It's something that can be achieved, but it's usually been done using molten salts. So it's quite an expensive, quite high energy process as well. So that's not really ideal. That said, it can be done using non-aqueous solvents at room temperature or lower temperatures, as this paper managed, these guys achieved. And it's actually not dissimilar, the molten salt idea is not dissimilar from the production of aluminium. One of the kind of more promising aspects of that is that actually more recently people have found ways of electro deposition of aluminium at room temperature under ambient conditions, particularly using things called ionic liquids, which are a slightly unusual kind of modern type of solvent in effect. So there is definitely potential there. Okay, so electrowinning or electrorefining is one possible method for the production of, for the relatively cheap production of high-grade material, but there are others. So you've got things like acid leaching, this thing called solvent refining, or vacuum refining. But each of these has problems, and they all typically tend to be quite high-energy processes, so they tend to be quite expensive. And really, the identification of low-temperature methods is actually really quite a serious challenge, and it's a kind of major problem, really. Okay, so just a few conclusions then. So in the first instance, photovoltaic module recycling and the refining and upcycling of the constituent materials is a really, really important area for the research and development, particularly as we get more and more modules which come offline, come to the end of their life in the coming decades. Finding the economic means for the production of high-grade materials from end-of-life modules is really important. That will mean that we can actually produce a sort of cradle-to-cradle system for the manufacture of new modules, and it will also mean that we can get away with using fewer and fewer virgin materials in the production of these devices. And key to this, I think, is going to be finding a low-energy method for the refining of metallurgical grade silicon. But this is a really, really significant challenge, and it's definitely quite a difficult thing to be doing. Okay, thank you very much.